Welcome to today's presentation. In this session, we will explore LeetCode problem number 1163, last substring in lexicographical order. This problem challenges us to think creatively about string manipulation and optimization. Let's dive in and uncover the best approaches to tackle it. In this problem, we are tasked with finding the last substring in lexicographical order from a given string S. To clarify, a string T is considered lexicographically larger than another string U if, at the first position where the two strings differ, T has a character that comes later in the alphabet. For example, B is lexicographically smaller than C. Additionally, if two strings share the same characters but one is longer, the longer string is considered larger. The input to this problem is a single string S composed of lowercase English letters, and the output is the lexicographically largest substring of S. Let's look at some examples to better understand the problem. In the first example, the input string is S equals ABAB. To find the solution, we consider all possible suffixes of the string, ABAB, BAB, UB, and B. Among these, the suffix BAB is lexicographically the largest, as it starts with a B, which is larger than a, and no other suffix starting with B is larger than it. Hence, the output for this input is BAB. Now, consider a second example where the input string is S equals LeetCode. For the string S equals LeetCode, the possible suffixes are LeetCode, EatCode, EtCode, Code, Code, Ode, D, and E. Among these, the suffix code is lexicographically the largest. This is because it starts with T, which appears later in the alphabet than any other starting character in the remaining suffixes. Therefore, the output for this input is Toad. Now, if we take a string consisting of repeated characters, such as S equals ZZZZZZ, the result is slightly different. In the case of S equals ZZZZZZ, since all characters are identical, the entire string ZZZZZZ is the lexicographically largest suffix. This is because no matter which suffix we select, it will contain the same sequence of Z characters, and the longest one will always be considered the largest. Moving forward, let's review the constraints and edge cases for this problem. The string length s.length can range from 1 to 100,000, and the string consists exclusively of lowercase English letters. These constraints mean we need an efficient solution to handle very large input sizes. Let's now explore some key edge cases. One edge case to consider is when the input is a single character string, such as S equals A. Here, the only possible suffix is the string itself, so the output is A. Another scenario is when the string consists of identical characters, like S equals AAAA. In this case, the entire string is the lexicographically largest suffix. A more challenging case involves strings with maximum length, such as S equals *50,000. In such cases, an efficient algorithm is critical to handle the large input size, and the solution would involve identifying the last occurrence of the lexicographically largest character, which is B in this example. This highlights the importance of optimizing for both correctness and performance within the given constraints. When tackling problem number 1163, last substring in lexicographical order, it's natural to start by considering simpler approaches. One such approach is brute force. The intuition here is straightforward: generate all possible substrings of the string, sort them lexicographically, and return the last substring in the sorted order. While this is easy to conceptualize, it quickly becomes computationally expensive. Generating all possible substrings for a string of length n requires n squared time, and sorting them adds even more complexity, leading to a total time complexity of n squared * log n squared. This is clearly impractical for large strings. Another approach to consider is the sliding window technique. Instead of generating and storing all substrings, this method involves comparing substrings of the same length as we iterate through the string. By keeping track of the largest substring encountered so far, we reduce memory usage. However, the substring comparisons themselves remain costly. Each comparison can take n time, and since we might compare for every character in the string, the overall time complexity is n squared, in the worst case. While an improvement in memory usage, it still struggles to scale for large inputs. The sliding window approach, while better than brute force, is still limited in its efficiency. To address these limitations, we turn to a more optimized solution, the greedy approach using two pointers. This method takes advantage of the lexicographical properties of the string to minimize unnecessary comparisons. Here's how it works. We use two pointers, I and j, to track potential starting points of the largest substring. Starting with I at 0 and j at 1, we compare the characters at these positions. If the character at j is greater, we move I to j since we've found a better candidate. If the characters are equal, we continue comparing subsequent characters until a difference is found or one substring ends. Additionally, an offset pointer k helps us skip redundant comparisons entirely. This systematic approach ensures that we only examine the necessary substrings and skip over portions of the string that cannot yield the desired result. The result is an impressive time complexity of O(n), as each character in the string is processed only once. The space complexity is O(1), as no additional data structures are required, making this method both time and space efficient. The optimized greedy approach using two pointers stands out as the best strategy for this problem. Its linear time complexity and minimal space requirements make it ideal for large input sizes. The key insight here is recognizing that we don't need to generate or compare all substrings explicitly. By focusing on the earliest mismatching characters, we can systematically eliminate substrings that cannot be the lexicographically largest. This observation allows us to skip ahead intelligently, avoiding redundant work. Comparing this approach to the alternatives highlights its efficiency. The brute force method, while simple to implement, is computationally prohibitive. The sliding window approach, though an improvement, still performs unnecessary comparisons. In contrast, the greedy method achieves O(n) time complexity by leveraging the properties of lexicographical order, making it significantly faster and more scalable. This balance of performance and simplicity makes the optimized greedy approach the most elegant and practical solution for this problem. To start, the problem asks us to find the lexicographically greatest substring of a given string S. A substring, as we know, is simply any contiguous sequence of characters within the string. Now, while the problem sounds straightforward, solving it efficiently is the real challenge. If we try to generate all possible substrings and sort them, the time complexity becomes O(n squared log n), which is impractical for large inputs. Instead, we need a smarter approach. One critical observation is that the last substring in lexicographical order will always begin with the largest character, or characters, in the string. This observation helps us narrow down the problem. Additionally, when comparing substrings lexicographically, the result is determined by the first mismatched character. For example, in comparing ABC and ABD, the decision is made because C is less than D. Using this insight, we can forego generating substrings and instead focus on comparing indices directly, which is far more efficient. To implement this efficiently, we use a two-pointer technique. Here's how it works. We use two pointers I and j to represent the starting indices of two candidate substrings. Initially, I is set to 0, representing the current best candidate for the last substring, and j is set to 1, representing the next candidate to compare against. We also introduce a variable k to track the character-by-character offset during comparisons. The algorithm proceeds iteratively. While j plus k remains within the bounds of the string, we compare the characters at positions I plus k and j plus k. If the characters are the same, we increment k to continue comparing further. If the character at I plus k is smaller, it means the substring starting at j is lexicographically greater, so we update I to j, reset k to 0, and move j to I plus 1. On the other hand, if the character at I plus k is greater, we shift j forward by k plus 1 and reset k to 0, since the current candidate at I is still better. By the end of the loop, pointer I will mark the start of the lexicographically last substring, which we can return using s, I. This approach offers several key insights. First, the use of two pointers avoids the need to generate actual substrings, dramatically reducing both time and space complexity. By leveraging the offset k, we skip over characters that are already known to be equal, eliminating redundant comparisons. The character-by-character comparison ensures correctness by determining lexicographical order locally, without needing to process entire substrings. The efficient movement of pointer j further optimizes the process by skipping over indices that have already been proven suboptimal. For data structures, we rely solely on the input string and three pointers I, j, and k to track indices and offsets. This decision minimizes memory usage and keeps the space complexity at O(1). Analyzing the time complexity, the algorithm operates in O(n), because each character is compared at most once, thanks to the strategic movement of pointers. The space complexity of this algorithm is O(1), since no additional data structures are used beyond the pointers. Now, let's consider some edge cases. If the string consists of a single character, like a, the answer is simply the string itself. For strings with all identical characters, such as AAAA, the result is the entire string since every substring is equal. When the string ends with the greatest character, such as abxis, the result is the suffix starting from that greatest character, which in this case is XYZ. Finally, for strings with mixed characters, like ABAB, the algorithm handles repeating patterns effectively, avoiding unnecessary overlaps or re-evaluations. Here's the Python implementation of this approach. The function starts by initializing I, j, and k, and uses a while loop to compare characters and adjust the pointers. Once the loop concludes, it returns the substring starting from the optimal index I. This concise implementation reflects the efficiency of the algorithm both in terms of time and space. This solution efficiently computes the lexicographically last substring of a given string using a greedy two-pointer approach. The key idea is to compare substrings starting at different indices and maintain the starting index of the best candidate substring. Explanation. 1. Initialization. I and j are pointers to the start of two substrings being compared. Offset tracks the character position within these substrings being compared. Initially, I is 0, first substring starts at the beginning, and j is 1, second substring starts at the next character. 2. Comparison loop. The loop runs while j plus offset is within the string bounds. For each iteration, if the characters at I plus offset and j plus offset are equal, increment offset to compare the next characters in both substrings. If s, I plus offset, s, j plus offset, it means the substring starting at j is better. Update I to the next valid position. To avoid overlaps, set j to the next substring, and reset offset. If s, I plus offset, s, j plus offset, the current substring starting at I is still better. Move j to start at the next character and reset offset. 3. Final result. When the loop terminates, I points to the start of the lexicographically largest substring. Return s, I. Efficiency. The algorithm runs in O(n) time as each character is processed at most twice, once by I and once by j. This is optimal for large strings where generating all substrings or sorting them would be infeasible. Edge cases. Single character strings, the loop doesn't execute, and the function directly returns the string. Strings with repeated characters, the algorithm correctly identifies the lexicographically largest repetition. Overall, this approach balances clarity and performance, making it suitable for competitive programming and real-world applications. This is the Java implementation of LeetCode problem number 1163, last substring in lexicographical order. The logic mirrors the Python version, using two pointers I and j to compare substrings, with offset tracking the current character being compared. Key Java differences include type declarations and the use of char-at and substring methods for string manipulation. To solve this problem, we aim to find the last substring in lexicographical order for the given string s equals ABAB. The approach starts by initializing some key variables. The length of the string, n, is 4. We set I equals 0 as the starting index of the current best substring, and j equals 1 as the candidate index to compare against I. The offset variable, which keeps track of how many characters match between the substrings starting at I and j, is initialized to 0. For the first comparison, we look at s, I plus offset equals s, 0 equals at and s, j plus offset equals s, 1 equals b. Since it is less than b, the substring starting at I is no longer a candidate for being the last lexicographical substring. Therefore, we update I to the maximum of I plus offset plus 1 and j, which is 1, then reset j equals I plus 1 equals 2 and offset equals 0. Next, we proceed to compare the new substrings starting at I and j. This time, s, I plus offset equals s, 1 equals b and s, j plus offset equals s, 2 equals a. Here, b is greater than a, so we discard the substring starting at j by incrementing j to 3 and resetting offset to 0. This eliminates the candidate at index j from further consideration in this round of comparisons. Now we move to the third comparison. Here, I remains 1, and j is 3. We compare s, I plus offset, equals s, 1 equals b with s, j plus offset, equals s, 3 equals b. Since both characters are equal, we increment offset to 1 and continue comparing the next characters. With offset equals 1, we now compare s, I plus offset, equals s, 2 equals it and s, j plus offset, equals s, 4. However, since j plus offset exceeds the length of the string, we stop here. At this point, the best starting index for the last lexicographical substring is I equals 1. Extracting the substring from this index gives us s, 1, smiley face, equals bab, which is the result for this example. Next, we look at another example, s equals LeetCode, to further illustrate the approach. In the example where s equals LeetCode, we start with the same initialization. The length of the string, n, is 8. We set I equals 0, j equals 1, and offset equals 0. For the first comparison, we check s, 0, equals L against s, 1, equals e. Since L is greater than e, we discard the candidate at index j by incrementing j to 2 and resetting offset to 0. For the second comparison, we again compare the substring starting at I with the one starting at j. This time, s, 0, equals L is compared with s, 2, equals e. Once more, L is greater than e, so we increment j to 3 and reset offset to 0. In the third comparison, we compare s, 0, equals L with s, 3, equals t. Here, L is less than t, so we update I to the maximum of I plus offset plus 1 and j, which is 3. We then reset j to 4 and offset to 0. This shifts our focus to the substring starting at index 3 as the new potential candidate for the last lexicographical substring. With the updated I equals 3 and j equals 4, we continue comparing substrings. First, we compare s, 3, equals t with s, 4, equals c. Since t is greater than c, we discard the candidate at index j by incrementing j to 5 and resetting offset to 0. Next, we compare s, 3, equals t with s, 5, equals o. Again, t is greater than o, so we increment j to 6 and reset offset to 0. The process continues with s, 3, equals t being compared to s, 6, equals d. Since t is still greater, we increment j to 7 and reset offset to 0. Finally, we compare s, 3, equals t with s, 7, equals e. As t is still greater, we increment j to 8, reaching the end of the string. At this point, the best starting index for the last lexicographical substring is I equals 3. Extracting the substring from this index gives us s, pet smiley, equals code, which is the result for this example. In the final example, we examine the input s equals zzz. Here, the string consists of identical characters. After initializing n equals 4, I equals 0, j equals 1, and offset equals 0, we compare s, 0, equals z with s, 1, equals z. Since the characters are equal, we increment offset to 1 and continue comparing the next characters. With offset equals 1, we compare s, 1, equals z with s, 2, equals z. Once again, the characters are equal, so we increment offset to 2. Next, with offset equals 2, we compare s, 2, equals z with s, 3, equals z. The equality persists, so we increment offset to 3. At this point, there are no more characters to compare. The best starting index remains I equals 0, and the last lexicographical substring is the entire string, s, 0, smiley face, equals zzz. This example demonstrates how the algorithm handles strings with repeated characters efficiently. The time complexity of the solution to LeetCode problem number 1163 is O, n, where n is the length of the input string. Let's break this down. First, the initialization of variables I, j, and offset is a constant time operation, which is O, 1. Next, we have the while loop, which ensures that j plus offset remains within bounds. Inside this loop, character comparisons between s, I plus offset, and s, j plus offset, are performed, and these are O, 1, operations. If the characters are equal, the offset variable is increment, which is also O, 1. When characters differ, the values of I or j are updated and offset is reset to 0, and these updates also involve constant time operations. The combination of these steps ensures that each iteration of the loop involves only O1 operations, which is a critical factor in determining the overall time complexity. A key observation here is that during each iteration of the while loop, either I or j is advanced, depending on the result of the comparison. This systematic increment ensures that the indices do not revisit the same positions, meaning the total number of iterations is bounded by the length of the string n. Therefore, the loop executes at most n times, and since each iteration performs constant time operations, the overall time complexity is O(n). Whether we consider the best, average, or worst case, the result is the same. Even if the comparisons are resolved quickly in the best case, or take longer in the worst case, the fundamental guarantee is that the total number of iterations will not exceed n, ensuring the complexity remains O(n). Now, let's analyze the space complexity of the solution. The algorithm operates with a space complexity of O(1), which means it uses constant memory regardless of the input size. First, the input string s is not duplicated or modified, and no additional copies are created. The algorithm directly processes the input string in place. Additionally, it uses only a fixed number of variables, I, j, offset, and n, all of which require constant space. Importantly, no extra data structures like arrays or dictionaries are used. By avoiding additional memory allocations, the space usage remains constant, and this is why the space complexity is O(1). Let's compare this optimized solution to a brute force approach. The naive method involves generating all possible substrings, sorting them lexicographically, and then selecting the last substring. This approach is computationally expensive. Generating all substrings requires O(n²) time since there are approximately n plus 1/2 substrings. Sorting these substrings adds another layer of complexity, requiring O(n²) log n² time due to the sorting process. Together, the overall time complexity for the brute force method reaches O(n² log n. Additionally, the space complexity is O(n²), as all substrings need to be stored in memory. In stark contrast, the optimized solution avoids generating or storing substrings, achieving a dramatic reduction in both time and space complexity. To summarize, the optimized solution reduces the time complexity from O(n² log n to O(n) by adopting a linear scanning approach. The space complexity is also reduced from O(n² to O(1), since no substrings are stored, and the algorithm uses only a fixed number of variables. Mathematically, the while loop iterates at most n times because either I or j is incremented during each iteration. Each iteration involves constant time operations like character comparisons and variable updates. With O(n) total iterations and O(1) operations per iteration, the final time complexity is O(n). This makes the solution both time efficient and space efficient, a significant improvement over the brute force method. When tackling this problem, there are a few common mistakes that can trip you up. One of the most frequent is relying on brute force to generate and compare all substrings. While it might seem straightforward, this approach leads to extremely inefficient time complexity, often O(n²), or worse, which becomes impractical for larger strings. Instead, the focus should be on identifying the lexicographically largest suffixes directly. Another mistake is misunderstanding how lexicographical comparisons work. Remember, lexicographical order is not based on string length or numerical order, it's based on alphabetical precedence. To avoid errors, use built-in comparison operators like AND, which handle this correctly in most languages. Lastly, many people unnecessarily slice strings during comparisons. String slicing creates new substrings, adding overhead proportional to the slice length. A better approach is to use indices or pointers to avoid this extra cost and keep your solution efficient. Now, another area where mistakes happen is overlooking edge cases. For example, strings with repeated characters like AAAA, single character strings like Z, or strings containing non-alphabetic characters can reveal flaws in your assumptions. Testing these edge cases is crucial to ensuring your solution is robust. Another common issue is sticking to brute force or suboptimal algorithms without exploring more efficient methods. For this problem, the two-pointer approach stands out as an optimal solution. It leverages the structure of the problem to achieve linear time complexity, O(n). To get comfortable with these advanced techniques, it's important to study their implementation and practice applying them in similar scenarios. In interviews, this problem often tests your ability to recognize patterns and apply efficient algorithms. It's a variation of suffix-related problems, so understanding how to compare suffixes lexicographically is essential. The two-pointer method is the optimal solution here, and mastering it showcases your ability to think algorithmically and optimize for performance. Additionally, a key question you might consider asking is whether the input string is restricted to lowercase English letters. This assumption simplifies comparisons and could influence your approach. Be prepared to explain trade-offs as well, such as why brute force is inefficient and how the two-pointer approach improves both time complexity and scalability. This demonstrates not only your technical skills but also your ability to evaluate and justify different methodologies. To deepen your understanding, you may want to explore related problems that involve string manipulation and suffix-based logic. For instance, LeetCode 5, longest palindromic substring, focuses on efficient substring comparisons. Similarly, LeetCode 2.14, shortest palindrome, also deals with transformations and string comparisons. Another valuable problem is LeetCode 1698, number of distinct substrings in a string, which ties into suffix structures and substring generation. Lastly, LeetCode 2.42, valid anagram, reinforces the importance of understanding lexicographical order. These problems build on similar concepts and can help you recognize patterns and refine your approach to solving string-related challenges. Finally, let's consider some alternative approaches to solving this problem. One option is to use a suffix array or suffix tree. These data structures pre-compute suffix information, achieving a time complexity of O(n) log n, but they require more effort to implement. This approach is particularly valuable in scenarios where you need to perform multiple queries on substrings. On the other hand, the two-pointer method is simpler to implement for this specific problem and achieves optimal O(n) performance by skipping redundant comparisons. While brute force is the least efficient, it has its place as a basic or preliminary approach, especially for validating results on smaller inputs. Each method has its trade-offs, so selecting the right one depends on the problem's constraints and your implementation goals. Great job! We've summarized the key aspects of solving the problem last substring in lexicographical order. Remember to practice and apply these concepts to similar problems. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!